Thank you. X. Okay. So that's as a real polynomial. It's a degree 2 polynomial. So what Gauss proof is actually in the following. So if you consider the polynomial with real coefficient, if this polynomial has complex solutions, then you can find always the complex conjugate. One, that's also the solution of those equations. And if you really want to factorize the polynomial inside of the real coefficient, then just take the pair, x minus alpha and x minus alpha bar. Then this is the real coefficient. And also you can show that this real polynomial is irreducible in F, in real coefficient. So maybe this is quite a good exercise. It must be very simple. It's quite clear. Okay. So now it's clear. Well, again, so I'll make an exercise here. So fundamental theorem of algebra implies that any irreducible polynomial with coefficient in real coefficient is linear or quadratic. So this is very simple. This is a little bit difficult, but if you use a fundamental theorem, so it has a, you can factorize the complex numbers, okay? And then it's a real coefficient, so one complex number, you can always find a complex conjugate ones, so you have a pair always. Then that product is a quadratic equation of real coefficient. And so you can always find that if you have a complex solutions, and then you can find complex conjugate solutions so that you get quadratic factors in real coefficients. Okay, so what does it mean? What does it mean? Yeah, probably it's better to postpone tomorrow. But modern mathematics, we have several notions of algebras, and one of the important notion is a field. And that means that you have the sort of the systems which you have addition and subtraction and multiplication and division. And what this means is, if you want to have some figure field which contains the real numbers, then the only possibility is real number or complex number. No more than that. This is the complete consequence of the fundamental theorem of algebra or this exercise. Yeah, it's expressed strangely. So, maybe you are tired, I guess. So, tomorrow I'll talk a little bit about the field. So, field is a sort of system of numbers, which is the same as rational numbers or
I'm sorry, but the correct version of your statement must be limited.
and like this. And you can always find the coefficient, polynomial with coefficient in some field k. And here you can find some polynomial. And then the problem is how you can find sort of the solution or root of this polynomials fx equals 0. What kind of numbers? So if you are lucky, you can find the solution inside of k. But if not, how you can find the numbers in general? And we already find that if you k is real numbers, then that only possibility is L or C. But for the Q, so rational numbers, the situation is completely changed now. So there are many polynomials, any degree, not many degrees, such that the polynomial, irreducible polynomial with coefficient Q of X. That's possible, any degree. So it's a completely different from the Q and L. And the Q is in some sense quite algebraic. And L is you need some limiting process to define the numbers. So it's slightly different from the Q itself. And the modern abstract algebra tells you that to find that kind of the extension. So, for example, this is irreducible. Inside of this, so you cannot factorize the two polynomial inside of kx. And then, what you can show that is factorize in certain ideals generated by this function, and this gives you another field. So that I have to explain tomorrow a little bit. And so that the point is, if you have some field and you have some irreducible polynomials, then you can always, if you extend the field, then you can always find the solution of this fx0 inside of this field. So in that way that you can always extend it in the field so that to get the solution inside of that. And the important point is if you have a real, then you only get C. So it's a very strong. So for Q you have many. Not many, but for each is a polynomial, you can find the field extension inside of actually the C, but it's different from C. So the fundamental theorem of algebra has many aspects, and one aspect is of course analysis, but the analytic ways. But the other part is purely algebraic ways. And what does the Gauss really criticize in his thesis is that, of course, he did not know that such a notion, first of all, and